Hello AP Calculus students, Mr. Record here, and in this video we are going to take a look at a rather important theorem that is very closely related to your first fundamental theorem of calculus, which hopefully at this point you have probably studied to some degree. So we're going to get right into this here. It's called the mean value theorem for integrals, and as you can see here in the box, it says that if you have a function f of x that's continuous on the closed interval, then there will exist a number c on that closed interval from a to b such that the antiderivative of f of x with respect to x evaluated from lower bound a to upper bound b is the same as f of c times b minus a. And so often students really don't quite grasp the picture that's sort of being portrayed by this equation, but yet go on to use a slight modification of this theorem and actually use it pretty effectively. But I feel like sometimes we're missing the boat when we don't really see what this mean value theorem is suggesting. And you might remember a mean value theorem associated with derivatives from an earlier part of the course. These are slightly different in what they're trying to accomplish, but yet their overall theme, I suppose, would be very similar. So let's go ahead and take a look at this. Let's focus right now on the left side of the equation, that antiderivative or that integral of f of x with respect to x from a to b. So what we've got is an interval that I'm just going to randomly, arbitrarily choose along the x-axis of my leftmost coordinate plane. It doesn't matter where I put that a and b. If you're following along using my notes, you put that a and b wherever you desire. And then of course we have a function f of x that I'm going to choose to make look something like this, something that's got a little bit of activity to it. Well, hopefully at this point you all realize that the antiderivative of this function from a to b is nothing more than the area under the curve above the x-axis between the a and the b. So I'm going to go ahead and color that in. And as I said, this is what we're looking at. This represents the left side of that equation. The amount of space that you see occupied by that yellow highlighted region is the left side. Now let's take a look at the right side. Now the right side doesn't really look like it has much calculus going on. It's f of c multiplied by b minus a. Well, as you can see, it still incorporates the idea of the a and b boundaries. So I'm going to go ahead and put my a and b in my picture on the right side. I'm going to try to make sure that I put a and b in the same spots as they were on the left side. Otherwise, the demonstration here, that wouldn't really be as factual. But then this theorem says that there's going to be a c value somewhere in between a and b. Now, for the purpose of this demonstration, I'm going to have to sort of estimate where I believe that c is going to be located. And just eyeing the function that I had given you, it's actually going to be somewhat in the middle. Now that doesn't have to be the case. I perhaps could have drawn a slightly different function where that wasn't going to work, but I think I can still convey the idea that I'm trying to convey nonetheless. Let's go ahead and take a look at the function f of x again, but what I'm going to do here is I don't want it graphed quite as vividly, so I'm going to just sort of dash it in to indicate that's where it's originally was located. And then, as I said before, the c value is going to correspond to a point that happens to lie on that function, who would of course have a y-coordinate of f of c. And then if you look a little bit more carefully at the disposition of this right side, you in a way have two different things that are being multiplied together. And if you'd allow me to sort of rename those two different things, the f of c could sort of serve as a height or perhaps a length, and the b minus a as a width. So what we've got here is a rectangle with this height f of c all the way across, and of course the b minus a you could serve as the width. Now it wouldn't matter if you flip-flopped L and W, because you know that the two dimensions will multiply together nonetheless, and they're going to make your rectangle. But if I then shade in this rectangle, because in essence we are finding the area, I have this green shaded region. And then if we step back and look exactly at what we see in the middle of this equation, we see an equal sign, of course, and then we can surmise that the yellow shaded region and the green shaded region are indeed the same. They occupy the same amount of space. And that's it. That is the mean value theorem for integrals. Now, the important part, in my opinion, about learning the mean value theorem for integrals, especially if you're in an AP calculus class, is what it sort of springboards into. And that's this next box that says the average value of a function. And it says if f of x is integrable on the closed interval a to b, and then the average value of f of x on that interval is given by 1 divided by b minus a times the integral of f of x dx from lower bound a to upper bound b. Now I want to remind you just a moment, because I know I switched the slide, what we saw previously. We saw that the integration of f of x from a to b was equivalent to f of c times b minus a. Now if you look very carefully at the two sort of relationships I have here, if we were to divide both sides of the equation I just wrote by b minus a, you would see that the left side is indeed this expression for average value of a function. And if you were to read through some of the information at the beginning, it kind of mentions that the average value could be assumed to be this function f evaluated at c. There is this c where that particular relationship exists. This is the relationship that students will see on the advanced placement test over and over again. It wouldn't appear just once, but you would likely see it on both multiple choice and some free response questions. So let's go ahead and take real quickly a look at an example 4a here, where we can use this particular relationship. Find the average value of f of x equal 3x squared minus 2x on the interval 1 to 4. Well, the average value of our function. And as far as like how you want to label, I don't really have a problem if you want to call this particular value f of c. I think that would be a good idea. I think a reader would definitely be able to follow along with your line of thinking. If you don't call it anything at all, it's not the worst thing that can happen. I think you're still going to get the answer correctly, but I do like to instill into my students that you should identify the things that you're finding in calculus. So we would start off with a 1 over b minus a, which would be 1 over 4 minus 1. You would integrate from 1 to 4 of this particular function, 3x squared minus 2x with respect to x. All right, when we simplify our 1 over b minus a, we of course get 1/3, and now we can start to integrate the 3x squared minus 2x, which is quite easy. The antiderivative of 3x squared would be 3x cubed over 3, which simplifies to x cubed, and the antiderivative of 2x would be x squared, 2x squared over 2, which simplifies to x squared. So if we use our boundaries of 4 and 1, we're going to be ready to plug them in. Plugging in our 4 to the third power, 64, 4 to the second is 16. and then subtract the quantity, what we get when we plug 1 in as a boundary. 1 to the third is 1. 1 squared is also 1. Those are going to cancel. So we're going to be left with 1/3 times 64 minus 16, which I believe is 48. And then 1/3 times 48 is going to be 16. So 16 would serve as the average value of our function f of x here on that given interval. So what does all of this mean, you might ask? Well, if we take a look at a graph here that I've rendered here on the TI Inspire here prior to doing the problem, you can see that I've got the function 3x squared minus 2x, and you'll notice the endpoints here that I've placed at the intervals from 1 to 4. And we've been able to calculate that the average value of this function is 16. But as I said before, what does that actually mean? Well, if we were to look at all of the y points on this curve along this interval, there are several of them. And if we were trying to find the average of those y values in a conventional means, we would have very little choice but to try to add them up and divide by how many that there are. Well, that's pretty difficult to do. You can't add an infinite number of things and then divide by infinity. But with the help of calculus, you can sort of do that. And that's exactly what's happened. And if you look at about where 16 would be, that would be somewhere in this vicinity here. And so if I move across, that there would end up being about the average value of the y that would lie on this curve. Now, we have a second part to the problem that asks us to find the values of c guaranteed by the mean value theorem for integrals for the above function on its given interval. And this is the part that a lot of students find some difficulty with, because you have to be able to sort of apply the information that you found in part A. So what you're going to do here, this value of c, well, the value of c is really just a value of x. And I don't have any problem if we want to go ahead and think of it as such. So we have our function 3x squared minus 2x. Well, we want to find for what x value this expression is going to be equal to our answer from part A. So it's basically thinking that 16 is the y value. Now what is the x value at that location? So in this particular instance, you just have a quadratic equation to solve. So we're going to bring the 16 over to the left. And then you're probably going to have something that either factors or doesn't factor. I would spend, maybe about 30 seconds to see if it factors. And if it doesn't factor, you can then always use the quadratic formula. But 3x squared is not going to give us a lot of options other than 3x and x. And if we play the values correctly with our 16, I think we're going to want to put our 8 here and perhaps our 2 there, so that the inside 8x could be negative and the outside 6x could be positive. That would give us our minus 2x. And then, of course, if we use our zero product property, we would end up with x is equal to 8/3, or possibly x is equal to -2. Now I know that the directions here indicate that there is the potential to have more than one value of c or value of x, but you have to be very careful that we pay attention to that given interval. And that given interval I'll rewrite here was 1, 4. So any time that you've got a value that's not going to lie in that interval, you want to omit it from your final answer. So the solution to this problem for your x, or if you wanted to then call it c, would be 8/3. That's the one that lies in the interval. Okay, but again, there can be more than one answer that lies in that interval. And if we go back to the graph here, what we're going to notice here is that when we achieved that 16, which is somewhere right around in here, that's happening when we're at about 2 1/3, or 2 2/3, I should say, right? 8/3. So right about here would be the y value of 16. Okay, so it's great to kind of see that graphically. But that's it. There's your first example of the average value of a function. Lots of problems that you can work with this particular concept in both the textbook and the notes. And I wish you the best of luck.